Okay, so we're still on this containerization and Docker topic, and will be for another 2 weeks, I'd say at least. And I want to start looking at these slides here. I started the last day talking about networks in Docker, and it actually arose in last week's lab as well. Just speaking of the labs, I'm not getting a whole lot of interaction from ye. I'm going to interpret that as good in the sense that ye are making progress in the labs. I hope that's the case. I'm sure it is. But don't let the labs slip on you, even though you're not submitting any work to me. Obviously, everything that we are doing in the labs will come to play when we start doing assignments and in the end of semester exam as well. And you might have noticed in the on Slack there, I just put up a message giving you the solution to an exercise. There was a small exercise in this lab here, the very first lab, and I gave you a solution to that exercise. So if you already solved the exercise, that's good. If not, then come back to me if you have any questions on it. There weren't any exercises in last week's lab, but last week's lab was quite long in terms of trying to get the applications up and running. There were two applications, if you remember, the user profile application and the employee management application, or at least they're the labels I put on them. So I'm assuming people were able to get both of those applications up and running. Um, or maybe there are questions that you might have for me right now on them. No? Okay. This week's lab is all about Docker networking, which actually you did a little bit of in last week's lab as well, but we will delve a little bit more into networking in Docker. So if I go to the slides, I guess these slides here. So I did introduce the um, this aspect of the Docker platform to you the last day. And it serves two purposes really. The reason Docker has lots of support for networking, albeit virtual networking, is any application that you develop in Docker tends to be broken up into a number of parts. And we build an image of each part, or we use images from Docker Hub. So either way, an overall application tends to be broken up into a number of containers. Now, presumably, those containers need to communicate with one another. So, hence, the Docker designers decided let's actually use the well-established rules of networking uh, and enable networking between containers in an application. Now, albeit our networks are virtual because our containers are not scanned or spanning multiple host machines, although they could be, in which case it's a slightly trickier problem. But we're assuming now our containers, the 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 um, the number of containers that make up our overall application are all running on the same host machine, but they do need to communicate with one another. Hence, that's why we need to leverage the support for networking within Docker. Also, when you're talking about multi-container applications, there is a part of the Docker tool called Docker Compose. Compose, as in we want to be able to compose our application from multiple containers. And we will look at Docker Compose maybe next week or certainly the week after. that will be the last part of Docker that we will look at. But for today, it's Docker networking. And I did mention this the last day that when you start up the Docker daemon on your uh, local machine or any machine, then by default it creates three networks, and they are named the bridge network, the none network, and the host network. And each of those networks, in fact, any Docker network has a name, but it also has a driver. And think of type as being what we mean by a driver. Now, whether it was a good idea or not, the drivers for the default networks are the same as the names. I never thought that was a good idea, but anyway, let me just get my pen here. So the default network whose name is bridge, its type is bridge. The default network whose name is known as type is, well, it's a null type that we often refer to it as the none type as well. And the host default network, its type is host. There are other types or drivers. In total, I think there are 7 different types of networks. But the only one that we're going to look at is bridge. We will look at the other two as well today, but we certainly won't be looking at any of the other types outside of the three that I'm mentioning here. Type bridge, type host, and type none. Um, in overview, a network whose type is none, and there is only one network whose type is none. You can't have multiple networks whose type is none. There's only one. And what it really means is, and you can add a container. We talk about adding containers to a network. You can add a container or containers to the none network. But essentially what it means is that that container doesn't have any networking access, which kind of defeats the purpose really, but there you go. There may be cases where you want a container to run an image that does some maybe processing, but it doesn't need to make contact with the outside world. In other words, it doesn't need any internet access. It doesn't need to talk, it does not need to talk to databases, which would tend to be running in another container. It doesn't need to communicate with other containers that might be running other applications. So if that case arises, you could actually uh, add such a container to the none network. The host type network or the host driver, whichever word you want to use, when you add a container to the host Docker network, then you're essentially adding the container as another service that is available on the host machine itself. And the IP address of that container will be the same as the IP address of the actual host machine. Okay. The third type, and it's the one that we're most interested in, is the bridge type network or the bridge driver network. When for and we can create we cannot create multiple none networks. We cannot create multiple host networks for obvious reasons. There's only one host machine, but we can create multiple bridge networks on the same host machine. And each bridge really comes from the networking device, a bridge device. For each bridge network that you create, the Docker daemon creates a virtual bridge interface to the outside world via the host interface. Obviously, the host machine has a network interface. You know, if it's not connected to the internet, then it doesn't. But obviously, we're assuming that our host computer does have a network interface to the outside world. When you create a Docker bridge network, uh, the Docker daemon creates, as I said, a virtual bridge interface which is connected to the host's network interface, and therefore that bridge has a connection to the outside world. And then each container that you add to a bridge network, it has network access or internet access via the virtual bridge device. And we'll see a kind of a visualization of that in a second. Okay, if we just step through these one by one, and uh, as I said, the only one that or the one that we're most interested in is the bridge one. But first of all, if we talk about the none network, so this is a network, a virtual network that's created by the Docker daemon. When you start it up, there is only one network, Docker network, whose type can be none. Um, and so it's the default one. So if I want to add a container to the none network, this is the way I do it. Docker run, of course. We use the minus minus network option, which you would have used in last week's lab. And you tell it which network are you adding this container to. And none here, if I go back, corresponds to this one here. And whatever other options that you want to pass to the run command. So the container in this case, it is part of a network and it has a network namespace. Uh, but it and other than local host, it doesn't have any other networking capabilities. So we could actually do that, right? Now, in this week's lab, we'll be using an image called the busy box image. It's a public image available on Docker Hub, and it has some useful networking utilities built into it. Mainly, ping is the one that we'll be using. So if let's say I want to start up a container using the busy box image, and I call my image box1, and I want to add it to the none network. Yep. So I'm just going to copy that. And before I run it, let's look at the status of my um, Docker desktop. I don't have any containers running, and I was playing around with this beforehand, so I already have the BusyBox image downloaded. But if I hadn't, then when I run this Docker run command, it would download it anyway, as you know. So Docker run, I'm running it in detach mode. I'm associating an interactive TTY terminal with it. The name I want to give it is box1. The network I want to add it to is that, and that's everything. Yeah. Okay. Uh, if I now do a Docker uh, inspect of box1, and you might remember from last week when you run the inspect command on an image, it tells you, amongst the other things, about the networking attributes associated with that image. So get an error. No such object. What did I call it? Box 3, sorry. Box 3. And here's the networking part or attributes associated with box 3. And you can see that it doesn't have any IP address. and it doesn't have any uh, network gateway associated with it. So that's my way of proving to you that this container just doesn't have any, it looks like it doesn't have any networking capabilities at all. I can do another proof of it to you. If I run the docker exec command, if I run this command here, and again, you've used this before. So if I run it on uh, my box three, sorry, probably box one. In fact, I think, let's see. I think the BusyBox doesn't support bash, so I have to run a standard shell box three. Okay, so I'm inside my container now, and the ping command, which I'm sure you've used before, if I try and do a ping of google.com, that server, then I should get some responses back. But of course, I don't, because uh, um, this container just doesn't have a gateway to the outside world. So the response I'm getting back there, okay, it's saying it's a bad address, but it's just because it doesn't have a access to this container doesn't have access to a gateway that allows it to make external requests to a remote server, in this case, google.com. Okay, so uh, exit out of that. And even if we do a Docker inspect, Docker network inspect of the none network, then that's true. It is running the my box tree container. And if we scroll up, does it give me anything? I wonder. Let's see. Oh yeah, see this part here. In normally what we would see here is some information about maybe an IP address range or something like that, but there's nothing. So that's again further confirmation that this none network has really doesn't have any networking capabilities. It doesn't have any gateway, etc., etc. I'm only repeating myself. Okay, so that's the none network. The next one is the host network. Now, I'll preface this by saying I cannot demonstrate the host network to you on this machine or any laptop that's running Docker desktop. But let's first of all just talk about it in general, right? So if I want to add a container to the host network, this is how I do it, same as before. I'm saying that the container is in the host network. It's essentially the container is going to have the same IP address as the host machine itself. Or if you want to send a request to a container that you've started like this, then the IP address that you would use to access that container would be the IP address of the actual host machine. And the image, I guess, let's look at the image here on the right. So this outer box here now is representing my host machine, okay, which in my case is my laptop, but in general, okay, it's your host machine. And the host machine has a network address and it has a network interface. Ethernet 0 tends to be the name that we would use for it. So that's the host machine's network interface. Here's your container. Okay, the container is going to be running inside uh, the Docker engine environment, which we've left out of this drawing. But and so the connection between the container and the outside world is directly via the host machine network interface. And so if this host machine receives a request to, let's say, port 8080, and if this container happens to be running an image that is listening on port 8080, then the request will go straight to this container because this container is listening on port 8080, and because it's on the host network, it's that port 8080 is really the host's port 8080. So there's no port forwarding or anything like that required. Okay, it has local loopback enabled, right? Um, it No other networking interfaces are supplied. Okay, so sorry, I went back there by accident. Um, the container is in the host network namespace. That's okay. There isn't a okay. That's all right. Processes inside the container have the same access to the network resources as those outside it. In other words, as those outside, meaning as any other any other applications that might be running on the host that you've started outside of Docker at all. Um, those other applications have the exact same networking capabilities as my container and or vice versa. Okay, it's like adding in a new service to your host. Um, the reason this doesn't work when you're using Docker Desktop is because the way Docker Desktop works is Docker Desktop, it does start a VM internally, but you don't have access to that virtual machine. The only time that this host network setup works is if you are running the Docker daemon on a Linux VM. Now, okay, that Linux VM is running on top of a host operating system, but the Linux VM, it will have its own IP address. And it's that IP address that you use to get at the container. So try and visualize it now. I have Docker daemon running on a Linux virtual machine, which is running on top of some host machine. But the way virtualization works is each VM does get its own IP address, which is separate from the host machine's IP address. And in that setup, when the Docker host network associated with the Docker daemon that's running on my Linux VM, that host network is essentially the same as the network that the Linux VM is running. When we're running Docker desktop on our machines, okay, the host in this case is my machine, but from Docker's perspective, the host is really the VM, the virtual machine that Docker daemon is running on. So we don't, so we can't use our desktop's IP address as a way of getting at a container that might be running within the Docker desktop environment. Not sure if that makes sense or not to you. What he will do in this week's lab is to try and use the host network, but it just won't work for the reason I've tried to explain. But when we eventually start running using the AWS environment and we start up an EC2 instance is an example of a Linux virtual machine running on top of uh, another operating system which we don't control, which is managed by the AWS environment. So we start up an EC2 machine, and within that EC2 machine, we will be able to start up the Docker daemon. We won't be running Docker Desktop because Docker Desktop is specifically for laptop machines. But we will be able to install and start up the Docker daemon on our EC2 instance. We'll then create a container and link it to the Docker host network. And we will be able to send requests to that container, provided we get the IP address of the EC2 instance. Okay, that's easy to say in words, but it's probably difficult for you now to visualize what I'm trying to get at there. But just keep it in mind when we do eventually get around to demonstrating this Docker host network type or driver. Let's move on to something I can demonstrate, which is networking. So the default bridge network is called bridge. And so if you want to add a container to that network, this is how you do it. Just specify bridge in the network option. And I'm saying, okay, the default network type, that's okay. The container, well, sorry, uh, the the default bridge network is assigned a subnet IP address range, and you would have seen that last week. So this is the way the bridge driver works. A subnet, an IP subnet range is assigned to each bridge network because we can create multiple bridge networks. You will do that in this week's lab. Each bridge network is assigned a subnet IP address range. And the idea then is that every container that you add to one of your bridge networks, it will get an IP address that is within the subnet range associated with that particular network. Now, the way when you create a bridge network, including the default bridge network, as I said, this is how we can kind of visualize it. What Docker does is it creates a virtual network interface, a virtual bridge network interface, which is represented by my orange box here. And this virtual bridge has a gateway to the outside world. It has a gateway IP address, which any container within it can use in order to communicate with the outside world. The bridge is linked to the host machine's network interface, which is this link here. And okay, that now gives us access to the outside world. Also, a container that is associated with a particular bridge network, it also gets its own IP address. If I go back to the previous screen, in the case of the host network, the container did not get its own IP address because we said its IP address is the same as the IP address of the host. In the case of a bridge, though, it does get an IP address, but that IP address is within the subnet range associated with a particular bridge because each bridge network on a host will have its own subnet range. Also, as well, because it has its own IP address, it gets a virtual Ethernet connection. The host machine has an Ethernet connection to the outside world. A container will also have an Ethernet connection, a virtual Ethernet connection, which is really why it has its own, what allows it to have its own IP address. And so with all of that now, that means that this container A has access to the outside world. If there were other containers within this bridge network that we're showing here, those containers would be able to communicate with each other because the bridge will actually perform routing, and it also performs what's called address translation, which you'll see what I mean by that in the labs. But it performs routing. So if I've got a container over here that makes a request to this IP address, then the routing logic within my bridge will actually route that request to the correct container. So I'm saying here, if I go back to the left, it's a standard subnet range. It's set up with network address translation, with a virtual bridge as a gateway. Okay, so this this serves multiple purposes. It takes care of routing within the subnet. It takes care of what's called address translation, and it also handles any requests from a container to the outside world. In other words, it plays the role of a gateway. Each container has a virtual, okay, we said that. So and you would have seen this last week. So maybe if I go on to the next slide, um, there can be multiple bridge networks within one Docker engine. Okay, and each is assigned a different IP address. That's okay. So if I quickly create some more bridges, so Docker network, create. Bridge one. Now the Docker network create, you can specify what type of network you want to create. Remember I said there are 7 different types of networks. We haven't looked at, and we will not look at the other types, but you could create instances of the other types as well. I've already said that you cannot create another network whose type is host or whose type is none. But if you don't specify a type, then it defaults to the bridge type. So my network here called bridge one, its type will be bridge. And if I do a Docker network ls, we can now see it. And as I said, I think it did this actually last week. Ls. So there's my bridge one. My network whose name is bridge one and whose type is bridge. And let's just create another one. Bridge two. If I now add some containers, so if I go back to here, when I don't specify, if I don't specify a network at all, if I leave this out completely, then by default, it will add the container to the default bridge network. Okay. Otherwise, I need to be specific. So minus minus network equals, let's say, bridge one. And let's call it box one. Box one. And let's put a box two in there as well. And what I'll do actually as well is if I leave this out, box three, oh, sorry, box three is already there. Let's get rid of that one actually. Box three. So the question is, where is box three now from a networking perspective? It's a question for anybody. Anybody want to guess from a networking perspective, where is box three? No. Well, if we go Docker, inspect, box three, it's on the network whose name is Bridge, and it has an IP address. It has a gateway, which is the bridges, which is the bridge networks gateway. It has an IP address. If I do the same for, let's say, box two, you can see, look, it's on the network whose name is bridge one, etc., etc. It has a gateway. It has an IP address. It has a gateway. The IP address, sorry, the gateway is, sorry, where's the gateway? Here, sorry, gateway 172.10, sorry, 172.18.1. So that must mean if I do an inspect of bridge one, actually the other way around, but it doesn't matter. So 172.18.1. Okay, and that matches up with what I'm told here. So IP address range is 172.18.00 dash 16. And when we looked at the IP address, or when we inspected box two, its IP address is consistent with the subnet range that's associated with bridge one. So let's say now, so that's the IP address. Sorry, I keep getting them wrong. This is the IP address 172.18.03. That's the IP address of box. Which one are we looking at? Box two. So if I do, let me see now, if I do an exec, just bring it up. If I do of box one, remember now, box one is in the same network, the bridge one network, as box two. So when I go into when I open up a terminal for box one, I should be able to ping the IP address of box two, which is 172.18.0.3. If I'm right, 172.18.0.3. Yeah. So let's see if that works. Ping 172.18.0.3. And you can see there is communication going on between the two. So that looks good. And equally, if I do a ping of google.com, that seems to be working. So I can get access to the internet. If I try to ping box three is not on this network. Now, I need to get the IP address of box three though. I need to come out and do an inspect of box three. Its IP address is 172.17.0.2. Yeah, 172.17.0.2. I'm going to go back into box one. I'll try and ping 172.17.0.2 and it should not work. Okay, doesn't work. So that has demonstrated that uh, it's isolating the containers based on their network association. Box three is on a different network from box box one. Yeah. Now the other nice thing though, so we are currently inside, where are we? We're inside box one. And you might remember box one is part of the bridge one network, and the bridge one network is a network of type bridge. But what's nice about, we would refer to bridge one and bridge two as custom bridge networks as opposed to the default bridge network. And what's nice is uh, custom bridge networks have support for address translation. In other words, if you, it will translate an IP, it will translate a container's name to its IP address, and it will perform routing on the basis. Routing obviously is based on IP addresses, but when we start pinging there, trying to remember the IP addresses of the other containers on the network, is a bit cumbersome. It would be nice if we could say ping. So we're inside in box one now, and box one and box two are on the same network. So if I do a ping of box two. By the way, everything I'm doing here now, you will be doing in this week's lab. Um, what the gateway, the bridge associated with my bridge one network, that bridge will perform what's called address translation. It will translate the container's name into its IP address and then perform the routing based on that. So if I go that, you can see that the two containers are actually talking to each other. even though I just specified the name of the container that I was pinging rather than its IP address. You do not get that feature within the default bridge network. You only get it within a custom bridge network, which is kind of unusual, but there you go. The default bridge only you can only refer to containers by means of their IP address. Nothing else works. Right. So as I said, all the kind of playing around that I was doing there is really what the focus of this week's lab is all about. I got back to my slides. The last thing we want to look at in relation to networking is actually something that you already know about, which is what's called port forwarding. And this applies when an external client wants to communicate with a container, and that container is part of a bridge network, whether it be the default bridge network or any custom bridge network that you have. And the way you achieve this is by um, instructing the Docker daemon when you start up a particular container to perform port forwarding for that container. And so maybe as I said, you've already done it, but so we've got an external client and it only knows the IP address of the host machine. As you know, of course, the IP addresses of the containers within a bridge network, those IP addresses are only usable within the bridge network itself. They're not usable outside the outside world. They're not kind of translated outside of the bridge network. So if you've got an external client, it can only use the IP address of the host, but it is specifying a port number. Now, the assumption is that when we started up this container, we asked the Docker daemon to perform port forwarding for this container. And that's okay. Internally, the Docker daemon uses a Docker proxy uh, process to do that for it. And so the way it works is, as you know already, I think, when this request arrives at uh, the host network interface, because the port number that is being used uh, is part of the port forwarding that you created for the container in my image, then, sorry, no, then that request will be handed over to the Docker proxy, and it knows that any request that came in to the host on port 8080, that should be forwarded on to whatever port the container is listening on, which in my case here, I'm assuming it's port 80, I think, although it's not obvious from the image. Is it? No, it's not obvious from the image. But whatever port we said the container is listening on when we started it up. And you know the -p option when you start to start a container. So we're forwarding external socket requests to a container. The requested port and the container's port can be different, and they can be different. Okay, they may be the same, but they can be different. The requested port is the port that my external client is using. So if I've got if container one is a web server listening on port 80, and the client sends a request to the host port 8080, then this is the sequence that it goes through, which I was kind of talking about there. I guess what I should have included in this slide as well is how do you set up port forwarding for a container, but it's using that -p command line option when you run the container, which you've seen already. And you will be doing that, I think, again in this week's lab, even though you've already experienced it. Right. That's all I want to cover. Next week, what we will look at is how do we actually build an image of our own application? Um, all we've been using so far are images that are available publicly on Docker Hub, but we'd like to be able to create our own images, and those images can communicate with images from Docker Hub if we've programmed our image correctly. So that's going to be the focus for next week. I think I'm up on time, am I? Yeah. Okay, I didn't really pause as I worked my way through that, but are there any immediate questions that you might have? No. So the lab for this week is this one at the bottom. And as I said, it's all about networking and all the stuff that I was demonstrating there. So I'm going to leave it at that if you haven't anything to ask me, and I will touch base with you in tomorrow's lab. So that there won't be any lecture tomorrow. It'll be a lab all the way through, but I'll be monitoring Slack from about 9:20, 9:25 onwards. Right. Bye for now.